Hello, in today's lesson we will talk about Compton effect, where a photon falls on an electron. Photon is scattered at an angle phi with an increased wavelength lambda dash, whereas the electron recoils at an angle theta with the x-axis. So this is the process that we are going to study. Here is a photon which will fall on an electron. Photon will be scattered in this direction with wavelength lambda dash. Incident photon had wavelength lambda. Scattered wavelength will have wavelength lambda dash. At an angle phi, it will be scattered, whereas the electron which is hit by this photon will recoil at an angle theta with the x-axis. So in a nutshell, this is what the process is at the level of an electron and a photon. In studying this process, we need some special relativity knowledge, especially two relations we will use. Let me summarize it before we start our analysis. What is relativistic momentum? Normal momentum, we know in Newtonian mechanics, P equal to mv, but when this v is very high, comparable to velocity of light, then P equal to mv, this relation is modified to P equal to mv divided by root over 1 minus v square by c square. But you can easily see that this relation will reduce to P equal to mv. Suppose v is much less than c. Then with respect to 1, you can neglect this second factor. Since square root of 1 is just 1, then P equal to mv. So we recover the Newtonian momentum. And the other relation that we will use is the relativistic energy, which is mc square divided by 1 minus v square by c square minus mc square. This looks very different from the Newtonian kinetic energy of half mv square, but let us check what happens when v is much less than c. We can write this as mc square and 1 minus v square by c square as 1 minus v square by c square square root as 1 minus v square by c square whole to the power minus half. And this one can be binomially expanded. So just keeping the two terms, mc square bracket 1 plus half v square by c square, higher terms bracket close, minus mc square. Then this mc square cancels with this 1 mc square. What remains is half v square by c square multiplied by mc square. C square cancels and we recover half mv square. So even though this expression for relativistic kinetic energy, it looks very different from our expectation of half mv square, we can still recover half mv square if we binomially expand this factor here. Okay, so this will be the two relations, relativistic relations, that will be used in our analysis. First, let us consider the energy conservation in this process. We know that energy has to be conserved before the collision. After the collision, total energy must be the same. The energy of the incident photon is hc by lambda. Energy of the scattered photon is hc by lambda dash. Kinetic energy of the electron we have just discussed, mc square 1 minus root over 1 minus v square by c square minus 1. So let us say this is equation 1. Now let us consider the momentum conservation. First, in the x direction, x direction, the momentum in the x direction, that is h by lambda. Momentum in the x direction is h by lambda dash cos phi, and momentum in the x direction mv by root over 1 minus v square by c square cos theta. So that completes the momentum balance in the x direction. Let us balance momentum in the y direction. There is no momentum in the y direction before the collision, but after the collision there is a component of this and one component of this. So 0 equal to h by lambda dash sine phi, so that is the sine component, and mv by root over 1 minus v square by c square, and the sine component of that, which is sine theta. So these are the three equations that we will need for our purpose. But let's just say little bit discuss about what was the situation in the early 20th century. At that time we had the model of J.J. Thomson, which was the plum pudding model, and if you think then electron is here, there is no concept of loosely bound or tightly bound electron. It is just in a plum pudding, and photon falls and it scatters. It cannot transfer any momentum to the electron, so it retains all its momentum. So photon's wavelength is unchanged, particles kinetic energy is unchanged, but the point is that incident photon, the energy of incident photon is much less than the mass energy of the particle. Okay, now what is the result of this experiment? The result will depend on the angle phi, because the detector is here, the angle phi, the detector is here, and we rotate the detector from here to here. So when phi equal to 0, so detector is here, we just see a single peak, that is the incident wavelength, or a single peak at the wavelength of the incident radiation. But when phi changes, for example phi equal to 45 degree, the peak at the incident radiation wavelength is there, but a second peak is developed. This second peak and the first peak, the difference is increases as we increase the value of phi. For example, when phi equal to 135 degrees, we can see a pronounced difference between the peak of the unchanged wavelength and the changed wavelength, and this is the delta lambda, which is the Compton shift. The wavelength of the scattered wavelength has scattered radiation wavelength has shifted from the wavelength of the incident radiation. So you can say that this first peak is due to the Thomson scattering, which was known before, but not exactly in the J.J. Thomson model, but in an atom we can have electrons which are tightly bound, and also some electrons which are very loosely bound, which are almost free electrons. So if when the incident photon hits an electron which is tightly bound to the atom, it cannot impart any kinetic energy to that electron. So the scattering becomes elastic. The photon recoils, photon is scattered exactly with the same energy with which it fell on the electron. So at that time the wavelength is unchanged, but at the same time the photon can also fall on a loosely bound electron of the atom. Then the electron will recoil and take part of the kinetic energy, and the scattered photon will have less energy than the incident photon, then the wavelength of the scattered photon will increase. So let us have some algebraic steps. So first let us square and add 2 and 3, that is the momentum conservation equations. We square and add, then here we get a cos square theta, here we get a sin square theta, so then theta can be eliminated. Okay, let us try to eliminate theta. We square and add, we have gotten rid of the theta here, but we could not get rid of phi because in this whole square, in the cross term, the phi survives, and that is the phi that will be there, that will survive till the last step of Compton scattering, that is the interference term of h by lambda and h by lambda dash cos phi. So that term is there, and then we have some other terms, h square by lambda square from here, h square by lambda dash square from here, and we have just simplified this m square v square c square by c square minus v square. So let us call this new equation as equation 4. Now let us look at the energy conservation equation here, energy conservation equation, divided by c, divided by c, divided by c, then we get h by lambda plus h by lambda dash plus mc within bracket 1 by root over 1 minus v square by c square minus 1. So let us call it equation 5. Equation 5. We can square this mc divide by c, this equation. We can keep this term and transfer this mc to the left hand side, h by lambda dash to the left hand side, then we get it in this form, and then square it. If you square it, then there are 3 square terms and 3 in cross terms. From the cross terms, from this cross term and this cross term, we get this term. These are the square terms. This is also a cross term, and this square term can be transferred to the right hand side. Then you see m squared c to the power 4 c square minus v square minus m square c square. We get exactly this, m square c square v square by c square minus v square, which was there in equation 4. So right hand side of equation 4 and right hand side of equation 6 is the same. Now we can just subtract 6 from 4. Then the right hand side cancels and gives 0. And from the left hand side again, some of the square terms, this term and this term, this term, this term, they cancel. But what we get is 1 minus cos phi term and this one. So just simplification gives lambda dash minus lambda equal to 1 minus lambda dash minus lambda equal to h by mc 1 minus cos phi. So this is the very famous relation of the Compton shift in the wavelength. This is lambda dash minus lambda. This is the shift in the wavelength. This is a quantum mechanical process because the photon is considered as a particle which is hitting the electron, and electron is scattering. So it has a photon has a particle nature, not wave nature. It is interesting that this equation was also derived independently by C.V. Raman. This is the paper, you can find it in the net. But at the end of the analysis, he used a different model of electrons, spherical gas model surrounding the nucleus, and at the end he substituted lambda is h by mv. That is the wavelength corresponding to uh, mass m or with velocity v. That is the de Broglie wavelength for mass m, and so he used this de Broglie wavelength, and then he could get the same relation as this with the different model of the electron. This is very interesting. I just came across this paper in the net, so I am giving you the reference. Indian Journal of Physics 357 1928. Okay, so now let us calculate this. Calculate this shift in wavelength. We know h is 6.6 to 10 to the power minus 27 arc seconds. M is 9.11 10 to the power minus 28 grams, and C is 9 into 10 to the power 10 centimeter per second. Then delta lambda becomes 0.0242. This is called the Compton wavelength of the electron, multiplied by 1 minus cos phi in Armstrong. So then for phi equal to 180 degree, we get the maximum, that is the double of this. Delta lambda max is 0.0484 at phi equal to 180 degree. Another example, suppose lambda equal to 100 picometer. Scattered radiation is viewed at 90 degree. What is the Compton shift? What is the kinetic energy of the recoiling electron? So Compton shift, we know h by mc 1 minus cos phi. H by mc, we can substitute the values of hmc. Then the shift is 2.43 picometer. But this is independent of lambda. Delta lambda is just dependent on the phi, that's all. So this is for any lambda, the shift is 2.43 picometer. But what is the kinetic energy of the recoil electron? Now we can see the energy balance. This will depend on the wavelength. That is 100 picometer, and then this is slight shift. So then we can calculate that initial kinetic energy is 12.400 electron volt. So photon lost 2.4% of its energy. Now let us read this. Amount of scattering is high for elements with low atomic number. For high atomic number, Thomson scattering dominates, where wavelength is unmodified and there is no recoil of the electron which is being hit. Unmodified, that is lambda minus lambda dash. The radiation originates lambda unmodified, that is lambda equal to lambda dash, and radiation originates from the bound electrons of the atom, whereas modified radiation lambda dash greater than lambda originates from the free electrons of the atom. Now let us just to end this lecture, let us look at the Compton wavelength of the electron. You can see from this relation of the shift in lambda, that is a factor h by mc. So this is defined as the Compton wavelength of the electron. For any other particle, we can similarly define the Compton wavelength of that particle. Suppose a new particle has mass mp, then Compton wavelength of that particle will be defined as h by mpc. Now why do we call it a wavelength? So what is there in h and m and c? There is no length. So let us check the dimensions of this quantity h by mpc. Dimensions of h by dimensions of m by dimension of c. H has dimension of angular momentum, which is ml squared t inverse. This has dimension of m, and this is velocity lt inverse. So m cancels, one of the l's cancel, T inverse cancels. So finally we get a length. So there is a characteristic length corresponding to, in the quantum mechanics, there is a characteristic length of a particle having a fixed mass. So this shows that h by mc has the dimensions of length. So let us stop our recording here. Thank you for watching.